So already you have studied about the prepositional logic. So today we will see first order logic today. So the first order logic can not only represent the complex uh, situations or logics which the earlier logic is unable to explain. So the PL was only explaining about the true or false of a statement, but it was not sufficient to represent the complex sentences or natural language statements, such as some humans are intelligent or Sachin likes cricket. So these are some of the sentences which cannot be explained, but with this first order logic, we can explain it. So how we can explain this, we will see. So first order logic is an extension to propositional logic, and it is uh, it is more efficient to use for explaining the natural language statements, and it is also known as predicate logic or first order predicate logic. So in first order logic, some of the terms are associated with it, such as objects, which are the things with individual identities, such as students, lectures, companies, cars, and then properties of the objects, which distinguishes the objects from each other, such as blue, oval, even large, then relations that hold among the sets of objects, like brother of bigger than outside, part of occurs after, owns visits precedes. Then there are functions which are the subset of relations where there is only one value for any given input, like father of, best friend, second half, one more than. So it is kind of subset. It is, you can say that it is a subset of relation. But there will be only one value for any given input. Before moving to this, we will see just two statements and the conclusion, and how uh, first order logic can explain the statement which the propositional logic cannot explain. So this we will see. I have written one note, so we will see that. Let me open it. of this you can able to see. I was earlier saying that there is limitation with the propositional logic. So I have written two statements. If it snows today, then we will go skiing. So let's say it as P. And then the second statement is it is snowing today. Let's say it's Q. And the conclusion we will go skiing. Let's say it's R. So if both the P and Q is true, then then the conclusion is we will go skiing will be true. But in the propositional logic, it was explaining that if it is true and false like that, is it not visible? Are we able to see it now? I've moved it more closer. Is it visible? I have shared it and I have focused it so it's visible now. Okay. Okay. So just go through it once. I have written it. So the previous two statements was holding as the conclusion will be valid. So now we will see another statement. So the argument which propositional logic cannot handle. So this we will see. Suppose one statement, everyone enrolled in the university has lived in a dormitory. And second is Mia has never lived in a dormitory. So two propositions we have. Suppose let's say P and Q. Then R will be Mia is not enrolled in the university. This statement we cannot break. So it is a declarative statement which neither true nor false or or not both also. So no rules of propositional logic allow us to conclude the truth of R. So we need more powerful type of logic called first order logic or predicate logic to explain this. Let's see how we can explain this. So that proposition R, I have explained it here. You can see. It will be more clear if we will go one by one. So you can just see how it is explaining that particular uh, proposition from the two statements we have mentioned. So it was not true and false, but it is explaining something else. And it is explained in a different way, not just like propositional logic. So if we will see again it later. Before that, we will see how the first order logic works and what are the terms, what are the syntax semantics are involved in that. So I will again move to our slide. As we have seen that the Mia is not enrolled in the university, that particular proposition or the sentence is explained in a kind of different way. So some of the symbols we have used that we will going to see. So as a natural language, first order logic has two main parts, syntax and semantics. So syntax will be the formal rules that define the structure of expressions in first order logic. And semantics provides the meaning to syntactic structures, typically defines using interpretations. For example, set of objects true or false based on the assigned relations. And the syntax will include the symbols, formulas, etc. So this both things will be included in the natural language so that we can explain it through first order logic. And the statements can be explained in first order logic in shorthand notation. So these things, hope you can see the basic elements of first order logic syntax are constants 1 2 a John Mumbai cat. So this you already know that constant value does not change. So this will be the constants, and then variables we can assign for a particular object x y z a b, then predicates brother father greater than symbol, function square root, left leg of, then connectives. These are the signs which we will be using. This will be the and sign, then or, then negates, then implies, then both side implying, then equality, and then quantifier. This is one quantifier and this will be another quantifier. So these two we will see in detail. So now the atomic sentences. So atomic sentences are the most basic sentences of first order logic. The sentences formed from a predicate symbol followed by a parenthesis with a sequence of terms. Here you can see the syntax, how we can write the atomic sentence. First predicate, then term 1, term 2, up to term n. So this will be your predicate. We have already seen in the earlier slide that predicate will be explaining about what is the relation among the terms we are using. So we are taking one example. Ravi and Ajay are brothers. So here the predicate will be brothers, and in bracket we will write Ravi, comma Ajay. Similarly, Chinky is a cat. So cat we will write a predicate, and in bracket we will write the name Chinky. So this is a very simplistic way how we can explain in first order logic. Then the complex sentences we will be seeing. So mainly the complex sentences will be difficult to understand. So from the atomic sentences, there will be different complex sentences. We can combine the atomic sentences in a form such that the complex sentences can be made. So the First order logic statement can be divided into two parts, subject and predicate. Subject is the main part of the statement, and predicate can be defined as the relation which binds two atoms together in a statement. In the atomic sentence also we have seen that predicate is there, so it is explaining about the relation between these two, Ravi and Ajay, and Chinky is a cat, so that was explaining it. So in the complex sentence here we have the subject as main part. In example, we can see that x is an integer. So x will be your subject and is an integer is the predicate, which will tell more, which will give the definition about the subject. Next, moving on to quantifiers. So quantifiers are the symbols to determine or identify the range and scope of variable in logical expression. So the quantifier will explain more about the uh, quantity of the specimen in the universe of discourse. So it will tell about the range or the scope, means how many and how much. So that kind of things it can be explained using the quantifiers in the first order logic. So there are two types of quantifier. One is your universal quantifier, which explains about for all, everyone, everything, and that is represented by the symbol this for all. And the existential quantifier, so it is explaining for some at least one, and it is denoted by the logical operator this. Just the symbol is kind of E. So first we will see the universal quantifier. As I've already explained, that universal quantifier is a symbol of logical representation which statement specifies that the statement within its range is true for everything or every instance of a particular thing. So it will explain about all or every or each of a particular element or particular variable. So it is read as for all, for each, or for every x, and it is denoted like this. Uh, in example, we can see that all men drink coffee. So we can write this in first order logic as for all x men x drink coffee. So this can be written, this statement can be written in first order logic like this. You can note it down for now. And then your existential quantifier. So earlier in the universal quantifier, it was explaining about the range. So it now the existential quantifier is explaining about the scope, where the quantifier has influence within a logical expression. And the universal quantifier was explaining about the specific set of elements being considered by the quantifier in that expression. And in the existential quantifier, we always use an or conjunction symbol like this. So if x is a variable, then the existential quantifier will be uh, written as this, or inside bracket we can write x, and it will be read as there exists x or some x for at least one x. For example, some boys are intelligent. So here we can write there exists x, boys x, and intelligent x. So some here you can see by using this symbol we can write the boys are intelligent. So we can combine this together using the and or conjunction symbol, and it will explain about the boys are intelligent. So these two are combined together to explain this particular sentence. Uh, Before moving on to this, the examples, we will see I have written something, so I will explain that also. So the complex sentences have the connectives, symbols used to combine or modify the propositions. So this will be the uh, not connective, then it will be disjunction, it is conjunction, disjunction or in conjunction, and this is the implication if then, and this will be the biconditional if only if. So this type of connectives we will be using to explain the complex sentences using first order logic. Then I've already explained about the quantifiers. So here I have written one more example. So this I have explained it. For every x, px is property or predicate that satisfy x such that there exists at least one y. We can write q xy is true for that particular x. Or we can say that every x has some associated y that satisfy the relationship described by q, provided that x meets the criteria specified by p. This can be explained in by using one example. Suppose we uh, are declaring with variable x for every student, then x is a student. There exists at least one course y that x has taken. Students are A, B, and C. So A has taken maths and science, B has taken history, C has taken maths and history. Then PA is true, A is a student. So we can write there exists y, q, a, y. A has taken maths and science, so this proposition is true. And the overall PA and there exists y, q, a, y is true. So this will be true for the student A. Then coming to the student B. Similarly, we can write and the B has taken history. Okay. It's better if you note it down. I will also share it, but you can note down the points or the topics which I have explained. So this I was explaining for the three students. They have taken subjects. So this uh, First order logic statement can be explained like this. For A and B, this can be like explained, and then we will see for C how it can be explained. So for overall B, we can write like this, and then for C, P C is true as C is a student. So C has taken maths and history, so it will be true. And the overall we can write PC, and there is YQCY is true. So the statement holds true for every student in domain ABC for the students in the class. This first order logic statement can be explained for the three students that are taking subjects, and like this we can explain. Now again, this we will move on to our slide. So further some examples we will see of first order logic using quantifier. All birds fly. So in the previous example also we have seen how we can write. So in this we can write it all birds fly. So for all x we can explain this as x as bird. So like this we can express it in first order logic statement. Then the second example, every man respects his parents. So we are using this symbol to denote all, every, this kind of things we can explain with this symbol. Then X man X respects X comma parent, where X is man, X equal man and Y equal parent. Then in the third example, some boys play cricket. So here the predicate is play X, Y, where X equal boys and Y equal game. So some, as we are mentioning some, so as already you have seen that how the uh, how this can be explained for some instance. So like that we can explain with this symbol, and then X boys X play X comma cricket. So we can explain it with this. Then in the fourth example, not all students like both mathematics and science. So here the predicate is like x comma y, x equals student and y equals subject. So here we are using the negation sign, this, and for all, because all, if we are writing all students, then only it was not used. So we are writing negation for not all students. So we are writing this not all x, and in bracket we are writing student x, then like x mathematics and like x science. So we are combining these two with an operator, because not all students like both mathematics and science. So these two subjects are combined for the liking of subject by the students. In the fifth example, we can see only one student failed in mathematics. So here the predicate is failed x comma y, where x equals student and y equals subject. So here you can write it as there exist x in bracket, you can write student x, then failed x comma mathematics, and y, as y we have written as y equals subject, and in bracket we will write again x is not equal to y, as we are writing here x equals student and y equals subject. So uh, this will tell you that not all the students will fail in mathematics, so only one student is failing, so that's why we are writing like this, it's not equal to y, and student y we are writing, and then failed x mathematics. So not all the students are failing in mathematics, so only one student is failing, that's why we are writing the statement like this. So it is somewhat complex as compared to the propositional logic, as the complex sentences are explained in first order logic, so it requires some more examples to be seen in order to get the idea. Again, we will see how we can translate the English sentences in first order logic or FOL. Every gardener likes the sun. So we are using this symbol for all x, gardener x likes x comma sun. So every all this we can explain with this symbol. Then second sentence is you can fool some of the people all of the time. So for some of the people we are writing this uh, symbol with x, and for all time we are writing all t, person x, and time t, and that uh, can fool x comma t. So just like the previous uh, FOL, we can write this also. Just we are replacing this with can fool, and this person and time we are writing, as here two things are mentioned, people and time, so we are taking person and time, x and t. Similarly, one another statement we are explaining with FOL, you can fool all of the people some of the time. So this in this two way we can write, it will be equivalent only. So for all of the people we are writing x, then some of the time t, person x, time t, and can fool xt. So this statement we can write in FOL, or the equivalent of this can be written as this, uh, for all x, person x, then for some time people can be fooled. So this statement we can write like this also. Similarly, one another statement, all purple mushrooms are poisonous. So all mushroom x we are writing, and the mushrooms are purple. So n purple x are poisonous x. So this way we can write this sentence. And in this statement, no purple mushroom is poisonous. So negation will be written. In these two types we can write. So this two will be equivalent only. Negation, no purple uh, x, and mushroom x, and poisonous x. So negation we are writing purple, since no mushroom is purple, but mushroom is purple mushroom is poisonous, so we are writing with an operator. So this uh, FOL, we can write the statement like this. Also, we can write like this also: for all x, mushroom purple x is not poisonous. So this will be more like the previous statement only. This is somewhat different. We are writing same meaning, but in somewhat different way we are representing it. You can write whatever you are comfortable with. And then one negation statement: Clinton is not tall. Just, directly we are using the negation symbol tall Clinton. So predicate we are using here, and Clinton in bracket we can write. So after this, we will again see that our previous arguments or statements where we have seen that and everyone enrolled in the university has lived in a dormitory. So that we will see how we can write in first order logic. I will share it. So in first order logic, we can write this particular logic in this particular statement in first order logic like this. For all x, ex, so it will be uh, it can be used for the x enrolled in university, then implies lx, x lived in dormitory. We are writing L and operator, then negation L Mia. Mia never lived in dormitory. Then again N negation E Mia. Mia not enrolled in university. So this we can explain in first order logic, and this way we can represent the whole statement. So this whole we can explain about everyone enrolled in the university has lived in dormitory for all individuals X. If X is enrolled in university, then X has lived in a dormitory. So just negation of this and writing Mia, it will explain about Mia never lived dormitory and Mia not enrolled in university. Just writing the negation of E. So this way the first order logic of the two statements we can write. Now we will see the truth table. So in Boolean also, algebra also, you have seen that we can explain in truth table. So here the prepositions we are using can be explained in truth table. So we will see into this how this truth table we can write. So there are two propositions and two variables. Let's say P and Q are there. So for P and Q, we can write the truth table. And here you can see in table we will write one P in one side and Q in another side. So first we will write true, 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 false, false, true, and then false, false. So this symbol I have already told you that it will be implying if P then Q, and the other proposition is negation of P or Q. So this will be represented in the truth table. We'll see how this can be represented. So first we will see P implies Q. So there we can write, you can see P is true and Q is true. So we are implying here true. Whenever P and Q are true, then the implies is also true. So we are writing the true here. Then if P is true, Q is false, then we can write here false. But when P is false, Q is true, we can write true. So this way it is represented. If P is false and Q is false, then P implies Q is true. Regardless of Q, just P is false, then we can write true. So this can be represented in the truth table. Just you remember the rules how we are writing it. Again, I'm explaining. Whenever P is true and Q is true, then it is true. If both P and Q are true, means if both P and Q are true, then we can write true. But if P is false and regardless of Q, we can directly write true. And if P is true and Q is false, directly we can write false. And if both are true, then directly we can write true. Then we will write the negation of P, just we will write the opposite of P here. True, then false, true, false, false, true, false, true. So just we are reversing it for the negation of P. Then for negation P or Q, then here, as you know, or for or, at least P or Q has to be true, so that we can write true, otherwise it's false. So we will see here this here P is false, then Q true. So since Q is true, so in OR statement we can write true. Both P negation of P and Q are false, so directly we can write false. And negation of P and Q both are coming true, so true. And negation of P is true and Q is false, so directly we can write true. So just once one true comes in OR statement, we can directly write true. If both false come, then we can write false, and both true are coming, then also we can write true. So this way we can see one example how we can write the equivalent propositions using truth table. So one more example we will see. This is another example. Here one third variable is there R, P, Q, R. So for 3 we are writing the truth table. P, Q, R, true, true, true. Then true, true, false, true, false, true, true, false, 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 true, true, false, true, false, 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 true, false, false, false. So directly we are putting true, false, true in the table. Then similarly we can write for P implies Q, we can write, as you already know, in the earlier example we have seen that if both are coming true, then true. if P is true and Q is true, then also it's true, just similar to the first one. It's again like this. Now, if P is true and Q is false, then directly we can write false. Similarly here also. Then P is false, Q is true, then directly we can write true. Similarly true. Then both are coming false, then we can write true, true. So for P implies Q, we can write here. And similarly for Q implies R, we can write, you can see true, true, so coming true, true, false, directly false, false, true, true, false, false, true, then true, 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 false, 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 true, true, false, false, then true. So just like the previous example we are writing here, it's same. So here we are having an operator between the two. So how an operator operates? So directly we can write from here, as both are true, so directly true we can write, but here one is false and one is true, so we can write false. Just in and if both are true, then only we can write true, otherwise it will be false. So that's why one false is coming, so we will write false. Here also false, false. Here both are true, so we are writing true. Here one is again coming false, then false. Both are true, 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 true. Till here we have seen how we can write the propositions in a truth table. We can explain it like this also. Now again we will see one another example. So again the conditional proposition P implies Q. So here, which among the converse, inverse and contrapositive are logically equivalent to the conditional statement. So this statement, how it is equivalent, this is equivalent or this, we will find out using the truth table only. So converse is written like this, just opposite of this proposition. Then inverse is the just the negation of this proposition, and the contrapositive is just this converse and the inverse of both combined. So it will be contrapositive. Now let's see how this we can verify using the truth table. Again, we will construct this as PQ, true, 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 false, false, true, and false, false. So we will take the negation of both P and Q like this, just doing the opposite of this. And then the implies we will write PQ. Just recall the earlier example, how we have written this. So here we will directly put it like this. So both are true, so it is implying P Q true. So true P is true, but Q is false, then we are writing false. P is false and Q is true, we are directly writing true, and both are false and we are writing true. Similarly, just take Q first and then P. The Q will be taken first and then it will imply P. So true, true will be true only. Then false, Q false, and P true. So it will come like true. Then Q true, P false. So it will come false. Then both are false. We will directly write true. Then just doing the negation of the two and then implying. So here we will take both from here. Negation of P and negation of Q we will write. So both are false. We will write true. Negation of P is false. We will, and but Q is true. We will write true. Then P is true. but Q is false, we will write false, and both are true, so true we can write. And similarly, we will take first P, then we'll imply Q, then we will imply P. So first we'll take negation of Q. False and false. So true, true, false, false, then false, true, true. Then both are true, so true. So what you can see from here, so this PQ, true, false, true, true, is equivalent to which of the these three statements. So here you will see the last contrapositive is just equivalent to our this conditional propositions, true, false, true, true. So these two are equivalent coming in the truth table. So the answer will be your contrapositive. Till now, anything you have to ask? In first order logic, what we have seen. You can also see the more examples, and so that you can figure out how we can explain in first order logic. So here it is looking somewhat complex. The sentences can be explained in first order logic is somewhat complex, but with solving examples, you can have the idea. Any question? Till now, whatever we have discussed, so this we can I can share with you in the group. You can see, and if you have any question, then you can directly ask in the group. will be more clear if you work out with the examples and see more examples. I will share with you this all and earlier topics also, so that you can see them in details. And this example and the rules, whatever rules we have seen how we can write. So with this, you can have the idea how we can write the sentences in first order logic. The truth table also can see with different type of propositions. Here we have taken only three, so more examples you can work out with. Any question? Okay, then we will conclude here only. We'll see the next things in the next class. And also I will share this in the group. Okay, thank you everyone. Any questions, then directly you can ask in the group. Okay, thank you.